So, hi, Merry Christmas from me as well. I'm Dimitris Barmpakos. I'm a postdoctoral researcher at the University of West Attica, and I will be presenting our work on the design and evaluation of sensor, but we as well incorporated the neural network for the prediction of various aspects of the sensor, so I will talk about it. Our lab focuses on manufacturing microelectronics with printing technologies. So one specific domain we work with is the flow measurement, flow or various fluids or airflow and so on. This is a domain that's very important for various fields, gas flow measurement, meteorology, biomedical fields, and so on. So the main concerns for this type of sensors are the accuracy of the system, the capability to work on a harsh environment, and the cost to produce such systems. Normally these are called MEMS, microelectromechanical systems, and they are very, very expensive to build because we need clean room facilities and very expensive laboratory equipment. We use printing technologies or mixed design with traditional imprinting techniques, so we try to minimize the cost as much as possible. And in this work, we propose a multidirectional thermal flow sensor with an innovative solution which will address some challenges during the measurement phase, and I will discuss about it. The main concept behind this principle of operation is a well-known principle. We have a central element here, which is called the heater, and current passes through it via electrical connections. And there is this phenomenon called Joule heating, which converts the electrical current to heat. So under no flow, there is an equidistant set of sensors placed orthogonally placed around the heater. So what happens when airflow passes from any direction to the system is that the thermal field actually moves. This is called the upstream, and this is called the downstream. Moves towards the downstream. So this is the angle of attack. And what we try to do mathematically is we try to extract both the angle of the attack and the actual magnitude of the flow. So we both sense the flow in SLPM, standard liters per minute, and the angle of attack. These are the equations we use. So as you can see, we are a laboratory that makes things. We don't write software. We are electronic engineers, but we have a mathematician as well. So he was responsible for the analysis of the data. We implemented this relatively simple structure. This is called Kapton or polyimide. It's a film that we can develop electronics onto it. These are the SMT platinum components. We use platinum because platinum has a very high TCR, meaning that its electrical resistance changes a lot with temperature variations. So we use standard PCB manufacturing processes to fabricate this device. Afterwards, we place this device in a channel. This has a calculated length so as to, this is the flow inlet, and we provide air from here. This length is calculated to have a Reynolds number so as this flow here is laminar. If we had placed the sensor close to the inlet, we have turbulent flows and vortexes and so on. Here the flow is laminar, so all the measurements are done in laminar flow, which is much more easy to both calculate and measure. This is our typical measurement setup. So actually this is the response for just the heater. This is a very old method of measurement. It's called the hot wire principle. You just heat an element, and as flow passes over it, you measure how much power you need to keep the temperature constant. This is a mode. It's called constant temperature mode. Or you could use the constant current mode. We just keep current source at 30 milliamps, and we just measure the flow based on the current drop. So this is a typical diagram for 0 to 25 standard liters per minute of dry air. We use an air compressor to provide dry air. Okay, this is what we call the response of the system. Actually, the system here is all the responses here are normalized. So for our heater, we have it under no flow, we apply flow to it, and we just measure how much time it takes to reach a steady state. And from that, we extract what we call the TAF, the time constant of the system. This is both for heating and for cooling the sensor, the heater, sorry. And as you can see, for all these LPMs, as it should, the system has the same response. It couldn't do otherwise because this is physics. So this is how we extract the actual angle of attack. So here we have taken measurements using this setup. We rotate this disk, which has our sensors, and the flow comes always from this angle. So we actually measure the direction of the flow as well. As you can see, it fits very nicely into sine and cosine graphs functions. So this was when we discussed it with our mathematician from the laboratory. He was very excited we can provide this data because he could work with them. Actually, what we did here is we took a set of measurements, and as you can see, there are variations from the ideal sine and cosine graphs. So his proposal to tackle this problem was to build a neural network, a single-layer backpropagation neural network, which correlates the 4 readouts of the sensors through this function. This is the neural network he proposed. So after that, we did a lot of effort into optimizing the neural network. And actually, we did a set of independent measurements as well. I will show it later on. As you can see, these are the main methods we use: Leibniz markup, Bayesian, Fletch-Powell conjugate gradients, and BFGS quasi-Newton. These were all done in MATLAB, I think using the toolbox. I'm not sure though. But of course, our contact is free for anyone if you want to discuss about them. And what we try to do is we try to approach the angle detection problem. So this is the actual flow direction, and this is the estimated direction, and we can extract an error from this graph. This is the best error. It's in degrees. So these are the 4 types of neural networks we tried, and actually what's important to note here is that for completely unknown data, a mean absolute error of 2.5 degrees was extracted, while for known data, I think the error was like 0.09 degrees. So for further accuracy, we need to first of all optimize this setup, because this setup is operated by hand, and human hands always induce errors to the system. So this needs to be automated. This needs to be sealed in a better mechanically more robust way. But other than that, compared to other systems we found in the literature, this is our system, and it's relatively in the range of, I would say, top 3 or top 5 systems. So in this presentation, just discussed briefly about the development of a low-cost flow sensor with multidirectional capability, and we implemented a supplementary artificial neural network for offline enhancement of the data. So the one keynote to take away here is that we need to do this inline and not offline. These were then done in another day. We will develop an embedded system to do this while we measure, to apply the neural network on site. This is a team of my laboratory in the University of Stockholm. And thank you. Yes. During the test, how much? I think the rotation were 6 degrees. Να το πείτε από εδώ. Έχει καταγραφεί.
exactly how it's ordered?
Από εδώ.
Both questions or the second one?
Both.
Okay. What was the first one? Sorry.
The first one was regarding how many degrees, how many measurements per.
How many measurements do you require in order to have each testing? How many measurements does it get into the neural network as an input? First question. And the second question is regarding if there is any overfitting in this type of data, meaning it's data derived from a material, heated or not.
So we are taking measurements per 6 degrees. So each dataset has spaces of 6 degrees measurements. And regarding the overfitting, because I'm not one who implemented the algorithm, I think he implemented the k-fold method, so he tackled this overfitting problem.
Okay.
So, yeah. Thank you.